Okay, so now we're going to solve this system of first order differential equations using the matrix method. So the idea is that we're going to first represent this as a matrix equation of this form, where A contains all the constant or function elements multiplying x1 and x2, which are the two functions we're going to solve for. And then these terms, so the derivatives, are going to be contained in another vector on the other side. So let's do that first. So we're going to have x dot 1, x dot 2, that's going to be equal to what? This is going to be equal to 3 minus 2, and this is going to be 2 minus 2. And the reason for that is that we need to move these two terms to the other side before we can set it up as this equation. And then that's why those signs are going to change. And then this is going to be x1, x2. So now that we have our matrix equation and we know what A is going to be, what we're going to have to do is find the determinant of the matrix A minus lambda identity matrix equals to 0. So we're going to solve this equation. And if you remember your standard matrix operations, you will know that the determinant is the following. So we're going to have 3 minus lambda minus 2, 2 minus 2 minus lambda, because this is the identity matrix, so it is basically just a diagonal matrix with ones on the diagonal and 0 everywhere else. So that's why we get this equals to 0. And now for this 2 by 2 determinant, we're going to cross multiply. So we're going to have 3 minus lambda times minus 2 minus lambda minus this, so that's going to be minus 4 equals to 0. And now if we expand this out, we should get the following quadratic equation: lambda squared minus lambda minus 2 equals to 0. And solving for the roots of this equation, we get to the following. So lambda plus 1 lambda minus 2 equals to 0. So now that we have our two eigenvalues, so our eigenvalues are going to be minus 1 and 2. We're going to find the eigenvector that corresponds to each of these eigenvalues. So how do we do that? Well, we're going to have to take each one at a time. And what we're going to do with this, actually I'm going to write this down at the top because we're going to need some space to solve this. So we're going to have lambda 1 equals to minus 1, and now what we're going to do is we're going to solve for the matrix A minus lambda 1 I. So the matrix is going to become 3 plus 1 minus 2, then 2 minus 2 plus 1, because minus lambda times minus 1, that becomes plus 1. So that's our new matrix, and this is going to become 4 minus 2, 2 minus 1. Okay, so what do we do now to find the eigenvector? Well, the eigenvector is going to be the solution to the following equation: A minus I lambda 1 I times the eigenvector 1 is going to be equal to 0. So what we're going to do is we're going to use row reduction here to find that value. So this is basically the same as saying this matrix here times the eigenvector is equal to a vector of zeros. So the way we can write that in shorthand notation is 4 minus 2, 2 minus 1, and then we're going to have this line in the middle, 0 and 0. So basically we're going to use row reduction on this to find the values of the eigenvector. So the first operation we can perform is we can get row 1 and then subtract 2 times row 2. And the reason for that is that if you subtract that, you basically get a whole bunch of zeros at the top, and then you get 2 minus 1. So we cannot reduce this further, so the one thing that we can actually notice from this is that we can actually get two sets of solutions here. So the first one would be, well, what is going to be the value of v1? So v1 is the first component in here. It's going to correspond to the first row. Well, v1 has to be equal to itself, because obviously this right here doesn't really tell us anything about V1, so that's the only assumption we can make. But what about V2 corresponding to row number 2? Well, for V2 we have what? We have, if I write this down as a linear equation, we have 2V1 minus V2 equals to 0. That's what the second row is representing, and this basically means that V2 is equal to 2V1. Now, if you notice something, both V1 and V2 are represented in terms of V1. So that means, so V1 is our free variable here. And basically what that means is that our eigenvector now is going to be 1 over 2, because they're both functions of the same. So that's going to be eigenvector 1. Now, eigenvector 2, corresponding to the second value of lambda, which is 2, can be found in much the same manner. So we're going to set up the equation for lambda 2. We're going to have a minus lambda 2 I equals to 1 minus 2, 2 minus 4. And then to find the eigenvector 2, we're going to set up the matrix, or the augmented matrix. This is what it is called, 0, 0. So we apply the same method as before, and in the end we should get the eigenvector equals 2, 1. Alright, so now that we have those two things, what can we do? Well, we know that the general solution to our equation should be written in the form of a sum of constants. So we're going to have C1 times eigenvector 1, which is 1 over 2, no, 1, 2, not 1 over 2, times e to the power of the first eigenvalue, which is minus 1, times t. And then we're going to have C2 times the eigenvector 2, so that's 2, 1, e to the power of the second eigenvalue, which is 2, so it's going to be 2t. And this will be the general solution. So if we wanted to find C1 and C2, we would need two initial conditions, so one for each equation, and then we would just apply it here and solve for C1 and C2. But it's pretty much the same method that you would use with finding the coefficients or the constants in any other general solution. So this is basically to illustrate the method, and this works for eigenvalues that are either real or complex. So it's a very useful method for solving systems of differential equations. We could have solved it using the method of substitution and algebraic manipulation that we used in previous videos, but this is just to show you that this is an alternative method. And in fact, this is more efficient because if you have a bigger system of differential equations, you can actually plug this into a computer and then just find the eigenvalues and eigenvectors in pretty much a few lines of code. And then from that, you get your general solution right away. You don't have to go through all the trouble of doing this whole procedure here. So in the next video, I'm going to illustrate how to reduce a higher order differential equation to a system of first order differential equations. And then using that, we can actually find a solution of this form for any order of the differential equation.